which R appears, and the remainder of my clausal form will be co-satisfiable with what I started with. Yeah, it will not change the satisfiability of this clausal form. If it was satisfiable now, it will still be satisfiable after I remove those clauses. If it's unsatisfiable now, it will still be unsatisfiable if I remove those clauses. So this is co-satisfiable with this clause over here. I could do actually the same thing, but I can do it for P bar. P bar appears negatively in two clauses, but it appears positively nowhere. So I can just say, let's assign false to P, so P bar will be true. So this clause disappears, this clause disappears. I'm only left with this one. Yeah? So I can do that and see that this is co-satisfiable with just this clausal form, and also in fact co-satisfiable with just this clausal form, but not logically equivalent. They are not logically equivalent. It's not the case that they have the same formula, because here P doesn't even occur anymore. So this clausal form doesn't care about what value you assign to P. You can assign true, you can assign false, doesn't matter. Here, we started with a clausal form where it was important that P be assigned false, so that each clauses become true. So the model where P is assigned true is not an interpretation where P is assigned true is not a model of this clausal form, but it is a model of this clausal form. So they don't have the same sets of models. Yeah? So this is an example of a simplification of a clausal form formula which preserves its satisfiability but does not preserve its set of models. Yeah? Please, this is an important realization. So if you think I don't quite see what's going on, stop me. I'll do one more example of a different simplification. Namely, if I find a clause that occurs in which there is a singleton set, so a clause that consists of exactly one literal, then in order for the clausal form to be satisfied, the literal must be true. There is no other option. The literal must be true. That means that, well, if there are other clauses in which this literal occurs, the same one, all those clauses are going to be satisfied straight away. Like here. Because I just say, let's set this literal to true, all clauses where the literal appears will be satisfied. But in this case, the converse may also occur. I didn't say that it was only the literal and not the converse. That was case 1. Now we're in case 2. We have a literal. I'm not saying anything about the appearance of its converse, but the literal is in a singleton set. So if I have a clause where the negation of that literal occurs, then by setting the literal to true, its negation will be false. So that part of that clause can't contribute to the truth of the clause anymore because it's false. So instead of removing the clause, we can remove the literal from that clause. Here is an example. Here I have a singleton set, your Q. Yeah, in order to satisfy the whole clausal form, I must set Q to true. Well, great. That means that this clause over here will already be true. Moreover, this clause over here, Q bar will be false because Q is true. So from this clause, I can remove Q. In other words, I can remove Q itself, this one, I can remove this one, the whole clause, and in this clause I can remove Q bar. So what am I left with? Just singleton. Well, a singleton set consisting of the singleton clause R. Of course, I could do the same thing here, but it's now already so trivial that everyone can see that you satisfy this by setting R to true, and you're done. So there are 2 more examples of such simplification on the slide, but I'm going to skip them for reason of time, but I think with the book and with these slides, it should be possible to understand what's going on here. I actually want to go to this week's material, because all this was in preparation to resolution. And resolution is another rule that also preserves co-satisfiability. And resolution is a rule that eventually will allow us to systematically derive satisfiability or unsatisfiability of a formula. So those others are simplifications, but resolution is the real trick here. So what does resolution do? Again, we are in this situation where we have clausal form formulas. Let's look at two clauses that clash. What does that mean for two clauses to clash? It means that one contains a literal and the other contains the converse of that literal. Any literal. If that is the case, then the claim is that we can take the union of those two clauses and remove both the literal and its converse from that union. So that actually reduces my clausal form formula, because I take out two of them and I create a new one. So the claim is that this resolution preserves satisfiability of your clausal form formula. So this is the theorem. If I have two clashing clauses, then I can, well, actually this is the union, so it doesn't, it grows actually, the whole set of clauses actually grows by applying this. But the claim is that this preserves co-satisfiability. So, in other words, the claim is that by throwing in this clause into the set that we already had, the set of models doesn't grow smaller. It can't grow larger because actually the clausal form set is larger, so whatever is a model after throwing in this extra clause certainly was already a model before I did that. Yeah, so you can, I hope that you agree with me that the set of models of this union can never be larger, can only be smaller or equal to the set of models of this thing over here. But my claim is that it doesn't grow smaller, that it's really the same set. Can we see that that is the case? So think of two clauses, and a clause is an OR of lots of literals, two clauses, and there's a literal that appears positively in one clause, negatively in the other. You are sure that whatever happens, this literal is either true or false. Can't be anything else. If it's true, then the clause in which it appears positively is thereby satisfied. Yeah? Whereas the clause where it appears negatively, I can scrap this one clause with this one literal, because that is not going to be satisfied. But the union of those two things is then also going to be satisfied due to the fact that the second part is satisfied. Likewise, if it so happens that this literal actually is assigned false, then the second clause can disappear. Yeah, because what it says is already done. Whereas the first clause, I can scrap the literal itself because it's false. Yeah? I hope that wasn't too much hand waving. The proof is also written down here. I will instead give some examples, but first of all, this algorithm over here. This algorithm is actually the resolution algorithm, which uses that resolution rule to eventually establish unsatisfiability or satisfiability of the formula. Yes, Henk.
What you essentially do is just take those two clauses,
yes,
and combine them, but take out all those literals in the control.
Yes, well, only one literal. You can't do it for two literals at the same time.
Okay.
They clash on one literal. They might actually clash on more than one, but you always take out only one of those.
Okay, so you end up with instead of those two smaller clauses, with one larger clause without that one literal.
That is correct. Exactly.
Okay.
Yeah.
Yeah, then I understand it correctly.
Yes. So here is an algorithm which is a fairly simple loop, which essentially says I start with a clausal form. Whenever I go through the loop, I pick two clauses out of my clausal form that clash, and which moreover I didn't pick before.
Do you still leave the original clauses
Yes.
in the set?
Yes.
Okay.
Good that you ask again. You have to leave the original clauses in the set because you might need them again to clash with other clauses and apply the same resolution to that clause together with another clause. So this loop says every time you have to pick two fresh clashing clauses. If there are no more fresh clashing clauses, then you're done. But as long as there are fresh clashing clauses, you continue, apply the resolution rule there, throw in the new clause with the clausal form, until either there are no more clashing clauses that you didn't have before, or the empty clause appears. So the resolution rule may result in an empty clause, and if you find the empty clause, you can stop. The empty clause can never be satisfied. If the empty clause is your clausal form, the whole clausal form can never be satisfied, so you're done. And that's the whole algorithm. The very stupid, very straightforward algorithm, which a computer can do. Let's see how that works in practice. For a small